Good morning, everyone. Happy Wednesday. We are going to be wrapping up the stability unit today. It'll only take a couple minutes. There's just one or two loose ends. So before I do that, are there any questions I can help you with? Okay, so we were talking about stability. We were talking about internal and external stability. We were saying that it's really, finding the stability of a system is the same as knowing if its poles are in the left or the right half plane. And that's a difficult proposition, especially if the coefficients of the polynomial that you're checking are themselves variables. And so that was the impetus for introducing the Routh-Hurwitz stability criterion. It is an algorithm that you can use to create an array. The array you can apply the test to, and the test will not tell you exactly where the roots of the polynomial are. It will tell you, are there any in the right half plane? Okay, so that was the last 2 hours summarized in 20 seconds. Where we left was this special case number 2. That is, if you end up with a 0 in the left column, then the algorithm in principle breaks because you're doing a lot of dividing by things in the left column. So the workaround is to take that 0 and replace it with epsilon, which we're eventually going to let get very, very small. And then you can carry on using the epsilon as your placeholder. So that's all well and good, except it doesn't account for this special case, which is case number 3, which implies a row of all zeros. So in the base case, there were never any zeros in the left column. In the special case, there was a 0 in the left column, but other things in the row were non-zero. And in the special case, there is a row entirely consisting of zeros. So this is a little weird, so I got to do a little bit of premature review here on polynomials. So let's make sure that we all understand. If I want to factor a polynomial p, that basically means I'm going to make a new polynomial a that if I multiply it by p prime, I get p again. So I would call this a factorization of the polynomial p into a and p prime. So this is the act of factoring. Just like you learned in algebra, taking a number and decomposing it into numbers that multiply to get you that number again, except replace number with polynomial. And that's all we're doing. And another fact that I'd like you to know is that if a polynomial is even, so if a of s is an even polynomial, well, a couple of statements are equivalent. That is, a only has even powers of s. So I'm using even in the integer sense, so 0, 2, 4, 6, whereas a of s is an even polynomial is in the signal sense, that the left and the right are mirror images of each other. And another consequence or equivalent statement for a of s being an even polynomial is that the roots of a need to be symmetric about the origin. So symmetric is a kind of a broad term here. So clearly if a is a even parabola, so in the form of s squared plus a constant, then you can have your roots here evenly distributed, where this distance and that distance are equal. But you can also have this situation in which your roots are complex conjugates, and that also counts as symmetric about the origin. And of particular interest to us, this also counts as being symmetric about the origin. Okay. So any questions on this? Basically, I'm kind of coming at you from left field here, but we're going to need these facts about polynomials in a second. The idea is that when you get this row of all zeros, this scenario only occurs when your original polynomial is factorable by an even polynomial. Okay, that's the only situation in which you can possibly get a row of all zeros in your Routh array. So let's actually walk through this example contemporaneously or simultaneously with explaining this special case. So this example, we've got a third order polynomial, so s to the 3, s to the 2, s to the 1, and s to the 0. And if we populate this serpentine style, we get 1, 2, 4, and then 8. And then here straight away, we get 2 times 4 minus 8, so that's 0. And then this entry right here is also going to be 0, because remember there are make-believe zeros out here. So we get a determinant 1, 2, 0, 0, which gives you this entry as 0. And if you were to keep doing this, you would get zeros in this row indefinitely. And so this is case 3, special case 3. So a row of all zeros. We can't get around this with the epsilon trick, I guess is what I'm trying to say. So how can we get around it? Well, the idea is this only happens if your original polynomial is factorable. And we call that polynomial that is factors into P of S the auxiliary polynomial. And as luck would have it, it's right here. So the key in this special case is when you get a row of all zeros, go to the next row above, and those entries, those coefficients, form the auxiliary polynomial, where the highest order term corresponds to this power of S. And this is why we write the powers of S out on the left-hand side of the array. So to make this concrete, the auxiliary polynomial in this example is 2s squared plus 8s to the 0. Okay. So again, it has to be an even polynomial, so I skip s to the 1, and so we get 2 and 8 as our coefficients. So a couple things. This implies that P of S, the original P of S, is actually factorable like this. So 2s squared plus 8 evenly factors P of S. The leftover, the remainder, I'm going to call P prime because I don't quite know what it is yet. But if I know the roots of A, what does that tell me about the roots of P? Actually, that's a good question. I haven't given that one away yet. So if I have this situation in that the polynomial P factors into A and P prime, how does knowledge of the roots of A tell me about anything about P? Too early for all this math?
You could divide it out of the main polynomial and get what's remaining. So we're...
Yeah, I mean, sure. We could take big P and divide it by A and get P prime. But so here, follow me here. If R is a root of A,
then it's the root of P?
Yeah, excellent. That's
okay.
Yeah. Then R is a root of P. Exactly, because what is a root? It's an argument that makes the function 0. And so if I make A 0, I make P 0. That's exactly right. Okay, sweet. So we now know that if we can get the roots of A down here, we have 2 of the roots of P. So these guys, here, I want to go somewhere else. I want to go over here. So this thing factors 2s squared plus 8 equals 0. So that's s squared equals -4. And that means the roots are plus or minus 2j. Okay, so since P was third order, we know 2 of the roots, and 1 is still missing. Okay. That 1, the one that is still missing, you could long divide. You could take A and long divide it into P and get P prime. In this case, P prime would be a first order polynomial, so its roots would be super easy to find. Or you could keep yourself in the spirit of Routh-Hurwitz and say everything here and below in this array tells me about A of S. Everything here and above in this array tells me about P prime of S. So this is going to be key because we can still do the Routh-Hurwitz criterion on the stuff that tells us about P prime. In particular, how many sign changes are there between these two entries? There are 0 sign changes, which means that the root of P prime is in the left half plane. Or I should say not in the right half plane. But since it's a real root, it will either be 0 or in the left half plane. So to finish off the procedure here, the third bullet point is what I'm going to do now. And that is, if you were to need to keep going, like if this was, say, an 8th order polynomial and it wasn't easily factorable like this, then what you can do is take the derivative of the auxiliary polynomial, and those coefficients get plopped into the row of zeros. And now, all of a sudden, we've gotten rid of our row of zeros, and we can continue on with the Routh array construction. So this would be the determinant 4 times 8 minus 2 times 0 divided by 4, so you get an 8 down here. So if you could not factor the auxiliary polynomial, in this case it was a 2nd order, so it was pretty easy to factor, you could walk down this array with the newly formed derivative line and continue your Routh criterion. So this would tell me that there are no sign changes. So this says that there are no right half plane roots of A. The payoff is that we were able to conclude this in this situation, that the roots of P are going to be either on the imaginary axis or to the left. Now, as engineers, I mentioned that having a root on the imaginary axis is usually a bad thing. And so in any of these cases, if you are in special case 2 or special case 3, you are going to have at least, or at best, you're going to have roots on the imaginary axis. So if the question is this system stable or not? If you run into either of these special cases, the answer is no. If the question is how unstable is the system, then you might have to crack into these to answer whether it's marginally stable or truly right half plane unstable. Any questions on this?
Professor, I was going to ask you, without just at first glance, those 4 numbers, could you immediately assume that it is passing the criteria with the row of zeros, or that row of zeros is kind of deceiving?
Which 4 numbers are you looking at?
The 1, 2, 4, 8, and then the row of zeros below that. Could you automatically assume because this is very simple polynomial, or is that kind of dangerous? Like, is that deceiving with the row of zeros below that?
So if I had started from scratch and gone 1, 2, 4, 8 in the top 2 rows, and then found I got a row of zeros, from that point, I'm able to say that the system is not strictly stable, because we're going to be in one of these 3 cases, yeah? Because I know that this means that there's an even polynomial that factors into P. And in all of these cases, like, none of these are good engineering cases. This is unstable, this is marginally stable, this is unstable. So for the majority of cases when you're trying to apply this, you can go ahead and stop and say, hey, something's wrong. I need to go back and check my system for stability. Unless you're trying to design an oscillator, in which case you actually want this situation. Did that answer your question?
Yeah, it did, yeah.
Okay.
Thank you.
Sure. Could you go over one more time the the thing with that you've boxed over here with the roots plus or minus 2j, it's filling in that left-hand plane bit.
Sure. So let me clean up the diagram here a little bit. So let's get rid of that. Let's get rid of that. Okay, so I guess let's start from here. So at this point, I know that the original polynomial, well, okay, from the very get-go, I know the original polynomial has 3 roots. Agreed?
Yeah.
Okay. So if I come across this situation with a row of zeros, that tells me that an even polynomial factors. And in this particular example, because it's third order, that even polynomial has to be second order, because it's the only possible even polynomial that could go in. And so if I can find the roots of that second order polynomial, then I will have 2 of the 3 roots of the original polynomial. And so that's what I did here, is these are the roots of the auxiliary polynomial, but that means they're also roots of the original polynomial, p. I could continue with filling in the Routh array, or I could say I already know 2 of the 3 roots, and that was the point of drawing this little line here, is if I keep going any lower, all of this is going to tell me info about A. Now, info about A is also info about P, but we've actually got all we need, right? We've got the exact root locations. Routh-Hurwitz isn't going to give us anything more. So that's why I turned my attention to looking above this line. And everything above this line is going to tell me info about P prime. Yeah, the remainder after I factor out A. And the info about P prime is there are no sign changes, which means that P prime only has, at worst, a root on the imaginary axis. So I guess let's be accurate here. This is left half plane or the origin. Or origin. Right, because the number of sign changes tells me the number of strictly right half plane roots. Since there were no sign changes, that means there are no strictly right half plane roots. Since there's only one root, it could either be at the origin or a negative real number. Does that make sense?
Yeah.
Okay. It's a little bit of process of elimination, which not everyone is comfortable with at first, but it's nice because we have a finite number of things that we're looking for, right? We have a finite order polynomial, therefore the process of elimination should terminate eventually.
Right. Thank you.
Yep. Okay, last little bit on Routh-Hurwitz is a warning, and that is that we led off, or up at the very top of this slide deck, we talked about how this is an unstable system on the right, whereas this is marginally stable. And in some contexts, that's an important differentiation. In this class, both of these are bad systems, but I do want to just allow for the possibility that sometimes you might want an oscillator which has multiplicity 1 poles on the imaginary axis. But Routh-Hurwitz won't be able to tell you if you get this kind of situation we were in here. Routh-Hurwitz won't be able to tell you if the roots are repeated or distinct, okay? It will only tell you that there are roots on the imaginary axis. So this is a super, I would call this an edge case. This is a very edge case. But I'd be remiss if I didn't tell you that it's a possible failure of Routh-Hurwitz to distinguish between this kind of marginally stable system and a truly unstable system. All right, that wraps up the stability unit.